Hello and welcome to Beamer Folk.
About 10 years ago, I resurrected my vinyl collection. I needed to obtain everything for this, and the first thing I did was to go out and buy a turntable. The turntable was second-hand and defective. When I got that home, I repaired that. I needed a moving magnetic cartridge, which I obtained. And the next thing I needed to get was a stereo phono preamplifier to plug into my ONKYO amplifier. Well, when I set all of this up, the first thing I noticed, and incidentally, this preamplifier cost about, 15 English pounds. And I didn't really expect too much from that. But anyway, when I plugged it into my ONKYO amplifier, the first thing I found is that the level was extraordinarily low. And so therefore, immediately I was thinking about building a buffer amplifier to this preamp and boosting the signal up. But of course, once I started thinking along those lines, I thought I'd actually see, even though the signal was low, see what the performance of this was like. It's not very good. For the money, it's okay, but it really didn't meet my needs. One of the things, and you can get these phono preamplifiers, they're all over the internet from a well-known auction site, and you can pick them up for £10. It's really quite cheap. So what's wrong with this? Well, this is not going to be a review of this product, but I quickly go through its failings. We know now that the output is extraordinarily low. The equalization curve within this phono amplifier was reasonably accurate but sensitive to output load. An amplifier's input impedance can vary from one amplifier to the other, and because the equalization curve can be altered, in other words, it's affected by the load, and it can change its performance accordingly. RIAA equalization stands for Recording Industry Association of America. And whatever you do with a phono preamplifier, you just have to make sure that whatever's going on with the left-hand channel is identical to the right-hand channel. The actual equalization can be slightly out, but as long as they are the same. And in this case, not only was there a difference between performance in the left-hand and right-hand channel, you had a difference between the two. The power supply was a 3.5mm jack plug, which meant that every time you plugged it in or poured it out, actually it shorted out the little adapter power supply that came with it. The tests that I did on this did indicate that actually for its money it's okay, but I would give it probably 4 out of 10. So I went on to design and build my own preamplifier, but I wanted to do this, as I always do, challenging myself even further. I wanted to do this as cheap as possible. And whilst I'm going to demonstrate how this is actually built, I thought it was quite a good idea that if somebody didn't have the money to have precision equipment, because that's what you need really to do this, is precision equipment, but they are expensive, and I believe that you can actually build a quality phono preamplifier with just a modern digital voltmeter, an inexpensive one. The one that I've got, I think, cost about £15, and an oscillator. Well, the oscillator I actually made myself. Of course, with a modern electronic meter, you cannot actually see the signal. It would be probably nice to have one of these inexpensive oscilloscopes, But nevertheless, I believe this can actually be done. And the RIAA equalization on my Phono preamplifier is very accurate. And I obtained that accuracy using a Wheatstone Bridge. Here we have my home-built Phono preamplifier in the middle here. Over here is my homespun DDS gesture-controlled oscillator. And down here we have an RIAA inversion circuit with precision capacitors and resistors. And over here is an inexpensive Unity meter, and it's a UTC 890 C for Cat Plus. Meters. I have, I suppose, in my workshop here about 3 methods of measuring capacitors. None of them are accurate enough. The methodology in which they use to determine a capacitor isn't quite good enough for an equalization circuit in a phono. So the only way that I could think of doing this inexpensively is to construct a Wheatstone Bridge. And that is how I've derived my accuracy when it comes to timing capacitors on the equalization. Most meters, by the way, are quite accurate when it comes to resistance. So providing you've got an adequate inexpensive meter, the resistance values you can be fairly confident about that they are accurate. So the resistances that I've employed are 1%, and it's just the capacitors that are the issue. You need from the meter a fairly low value AC input. That's important. You would probably need to use the frequency element of the meter. And just to get a ballpark value, it would be nice if you actually got a capacitance feature that would give you some idea of what you're dealing with. And the principle in which this can be constructed inexpensively is that you purchased just one of each critical capacitance value in a precision way. So you're buying in just 2 capacitors of fairly good accuracy. The 2 capacitors that I've got are plus or minus 0.5% of value. You could go up to plus or minus 1%, but those 2 capacitors are going to cost you at the moment somewhere between maybe £2 and £4 each. Contrary to popular thought, you don't actually need to use those capacitors within the RIAA. You only need to have one of each, and those plug into your Wheatstone Bridge. Just a couple of additional thoughts. One is that I thought the first preamplifier that I purchased was so grim that I wasn't prepared to actually sell it on to anybody else. Secondly, the oscillator, the DDS oscillator, actually needs a square wave output as well. A square wave is a wonderful thing when it comes to phono preamplifiers. It's a little bit like a doctor's stethoscope. You can determine a great deal what's going on and what's failing within your circuit with a square wave, so you need that option. The other thing is regarding the meter. I think I called it a UTC. It's not. It's a Unity UT890C+. The next point regarding the meter is the AC. You need the lowest AC value range here, and the frequency of modern meters are quite good at 1 kilohertz. It needs to be reading 1 kilohertz because most of the setup here is to do with 1 kilohertz. You know, your meter does need to be happy with reading a 1 kilohertz signal. I wouldn't expect much more out of a modern meter. It could probably read reasonably accurate up until about 5 or 6 kilohertz, but that's all we need. Anyway, that's that. The next thing we'll move on to is the Wheatstone Bridge circuit diagram, etc., etc.
And so to the bridge. We'll talk now about the Wheatstone Bridge and the need for me to calibrate certain capacitors for use in my Phono preamplifier. There's a lot of information on the web regarding Wheatstone bridges, particularly pertaining to DC. Well, this is an AC driven Wheatstone bridge. And if we have a look at the top left hand side here, we see I've got an AC input of 1 kilohertz at 1 volts RMS. If we look at the, and that impedance has to be quite low. I wouldn't go further than say 500 or 600 ohms. My oscillator is 47 ohms output impedance. So getting to the bridge itself, if one can imagine here for a moment that capacitor C1 and C2 are just resistors, and that all the resistors are, say for example, 10 k ohms. In the middle here, measuring between these two connections, is a voltmeter. Now I've drawn this as an analog voltmeter, but in fact I'm using, as you know, the Unity digital voltmeter with a maximum count of 6,000. So therefore I can read AC quite easily 10 millivolts. So we're looking at a millivolt AC meter here connected to these points here. Now, if all the resistors are identical, the same, as we said, 10 k ohms, this point here would be at half volts RMS, and so would this point be at half volts RMS. The meter would read 0. Well, as it's a digital voltmeter, it will still read 0. Now, if we change for a moment here back to C1 and C2, so they're not resistors anymore, they're capacitors. And if we determine the exact reactance of this capacitor and make that resistor, which is R1, an identical resistance to the reactance of C1, the level at which this point rests will be 0.707 AC volts RMS. And it's true of this as well. If C2, you determine its reactance and make R2 exactly the same reactance as C2, this will also sit at 0.707 volts RMS. And the meter will read 0. Now, if there is an increase in capacitance with reference to R2, this will measure that difference, so the needle will be slightly off from 0 volts. And that's true of C1 as well. So these two are in balance. The beauty of this system is that if we make C1, say 10 nanofarads, and have R1 exactly the same as C1's reactance at 10 nanofarads, but we made C2 15, that's 15 nanofarads, and that resistor here is identical to the reactance of the 15 nanofarads, this will still be at 0.707, and that will still be at 0.707, and the meter will read 0 still. So although this is a reference capacitor, you can be testing a value, which is the tested capacitor, you can be testing a value in a range that doesn't have to be identical to C1. It can be close to C1 as long as that resistor R2 is identical to the capacitor that you're intending to test. And that's its beauty. So for example, if you go over to right here, you've got the capacitors that are the precision capacitors that are required by my project, my Phono project. And let's say you wanted to measure the 47 nanofarad capacitor. Well, you might have a batch of, say, 10 47 nanofarad capacitors, but your reference capacitor, you don't have a 47 nanofarad reference capacitor, but you do have a 40 nanofarad reference capacitor. These are expensive, these very close tolerance capacitors. You might just have a 40 rather than a 47. Well, as long as you made R1 identical to the reactance of that 40 nanofarad with respect to 1 kilohertz, you can place your 47 nanofarad here to test a batch of them, as long as the reactance here of R2 is identical to now a 47 nanofarad capacitor. And if your capacitors that you have within your batch achieve an absolute spot-on precision 47 nanofarad, these 2 points will be at an identical voltage and you will read 0 on the meter. Now with AC, unlike DC, if the capacitance is not quite 47 nanofarad, by means of being under 47 nanofarad, maybe 46.8, or in fact a 47.2 nanofarad capacitor, because this is AC and there is no polarization as far as the leads are concerned, you will get the same reading if the offset of capacitance is either up or below. So in other words, if you get a 10 millivolts offset, you know for sure that the 47 nanofarad is not spot on 47, but you don't know whether it's a slightly higher capacitance or a slightly lower capacitance. Now in those circumstances, what I do is I test which side of that value this tested capacitor is on. And the way I do it is add a very small capacitance, usually a ceramic capacitor of say 50 picofarad or 100 picofarad, across your testing capacitor here, and just see whether the difference, your let's say 10 millivolts, drops to say 4 millivolts or increases to say 14 millivolts. If it decreases, you know full well that your testing capacitor is under, and what it actually needs, what it's actually desiring, is an additional little bit of capacitor, a make weight if you like, to bump it up to a value which is identical to the 47 nanofarad. Now, I hope I've explained that well. This is a nifty bit of circuit, and you can create high precision capacitances using just one precision capacitor. Now, if you look at over here on the right hand side and look at the capacitances that are required, they are here and their quantities are here. So what you need is, in the first place, is a capacitor for the inverted RIA circuit. You're only making one of those circuits, so you only need one capacitor of this value, 36.3 nanofarad. This can be constructed using a 33 nanofarad capacitor plus a 3.3 nanofarad capacitor. And what this system relies on is you either buy or you have in stock a quantity of capacitors. And you can buy 10 or 20 capacitors very cheaply. So what it relies on is buying a small quantity, maybe 10 or 20 capacitors, and finding those capacitors that are actually within that batch spot on. Now, most audio people really love polypropylene capacitors. It really is a desirable audio capacitor. In my humble experience, I personally haven't experienced sound differences between mylar or other film capacitors and a polypropylene capacitor. But if you feel that you would like to buy polypropylene capacitors, then please go ahead and do so. But I have stock of a number of film capacitors, none of which are polypropylene, and I don't have a problem with putting a film capacitor in there. And in fact, if I need to make up the capacitance slightly, I will even add a very small, maybe 50 puff or that sort of level of a ceramic capacitor. I don't worry about that, and I don't notice any audible difference or performance change in doing so. Okay, so what we need to do now is look at the next capacitor, which is the 10 nanofarad. So we need 10 nanofarad, and we need 3 of those. One for the inversion AA and one for each channel of the preamplifier, so that's 3. And we also need, as I've mentioned before, 47 nanofarad. Well, as it's for the left and right channel only, you need 2 of those. So what reference capacitors? I said to you at the beginning, you only need 2 reference capacitors to do the whole of this project. One of which most certainly would be a 10 nanofarad. So that's your first purchase, is a 10 nanofarad reference capacitor. Now the second reference capacitor, you could, if you look at this, you could think to yourself, you want a 47 or you want a 36.3. Well, you don't. Actually, it can be near those 2 values. And as you've noticed, they are actually quite close, within 10 nanofarads. So I think I would be inclined to buy a 39 nanofarad, that's 39 nanofarad capacitor, because the 39 nanofarad capacitor used in the reference position can reach up to 47 without difficulty, or reach down to a 36.3. As I said, it doesn't, C1 and C2 do not have to be equal. They just have to be within near reach. It's not wise to make your reference capacitor, say 10 nanofarads, and expect it to be reading accurately a 47 nanofarad. But when you're looking at 39 nanofarads, you're somewhere between the 2, aren't you? And close enough. Anyway, I hope that is of understanding. And I'll move on now to probably demonstrating this AC-driven Wheatstone Bridge. I have to say I've totally failed in explaining the right-hand side of this diagram. If we look at the capacitors here, say the 36.3 nanofarad capacitor here, its reactance at 1 kilohertz, precision reactance, is 4.384 kiloohms. And to make that value exact, we have to live in the real world. And the resistive values to construct that are these resistors here. You've got a 6K in parallel with a 12K, which is in series with a 22R and in series with another 22R. And that makes 4.3844 KO. And as you can see, that's pretty good. But I've had to use 4 resistors here. And you could probably, by fiddling around with resistance values and paralleling, probably achieve a 3 resistor combination that will probably be closer or equal to that. And it's true for the other 2 capacitance values. What I've done here, I've created the ideal, which is the precision reactance value here and here, and then constructed the practical real world values here and here. And for the 10 nanofarad, you've got 15.915, and I've managed to achieve, by using 22 in parallel with 56k plus 120 ohm, I've managed to achieve, 15.9149. Not bad, actually. And finally, the 47 nanofarad, you've got a reactance here, a precision reactance of 3.386, and I've achieved that by paralleling 4K7 with 12K plus a series resistor of 10 ohms, and that equals, 3.387. Very slight positive error there, 2.4. And as I said, if you're prepared to spend a fair degree of time, you can construct resistors to maybe get closer than these values, but who knows. Anyway, so I thought I would explain that bit of it, and that's complete now. And I'll get on to, as I said, demonstrating this wonderful AC-driven Wheatstone Bridge. This is Beamer signing out for now.